the inverse transformation is basically just interchange prime, not non-prime. That is kind of straightforward, right? Whatever we call it prime before, if the inverse transform, just change prime to non-prime. You understand what I'm saying? So for vector, uh, the transformation, we're saying that if the for counter vector components in prime, whatever the notation is slightly different from the, the other equation. I think I'll stay with the before, the equation, the notation before. The I is partial x pi r partial x j j. Right. So that's if it transform like that, that's contrarian vector. Right. So that we talk about. And the topic about the inverse transform is just basically just changing pi to non-pi. So the equation should be exactly the same. So whatever you see pi becomes non-pi, right? Non-pi becomes pi. Right? That easy enough, right? And the idea is that if you combine the two, obviously you do it successively, then you should recover whatever you have, say a pi I involving a superscript j, right? Then you substitute this into that, then you can check that you can partial I plus xj. Now this a becomes j, so you change this I to j. So partial xj. Obviously that you cannot use j, you can just change it to k. Right. Now j is sum because you repeat the index sum. So this is like using the chain rule. This is partial x prime I plus x prime k. And this derivative obviously is just a conical derivative. And sum over the k using the conical derivative. The a prime I equals a prime. Right? So you can check that that is the correct transformation. We inverse that, which should be trivial because the what we call pi and non-pi are just arbitrary. So whatever we call it, it's just the two coordinate system, whatever we call them, that's fine. So we call it pi, non-pi, non-pi, pi. That's just that's just checking some trivial expectation. Yeah. Yeah, I think that's at the end of this subsection, we talk about a misconception that but anyway, that's trivial. And the last equation is about the property that we're staying with Cartesian coordinates. So that is just a property in the Cartesian coordinate. This transformation matrix satisfies the basically this one or either one or this one or that one. They are they are they are interchangeable. The indexes it's if you change exchange I and j is exchange pi and non-pi, that actually the same. But this is just for the Cartesian coordinate, and that is exactly the same relationship that we showed before at the very beginning. We showed that for the Cartesian coordinate inverse of the matrix, transformation matrix is the same as its transpose. And that is exactly coming from this one. But this is just only for the, only for Cartesian coordinate. Later on in section 3, we talk about generalized or general coordinate or the general geometry. Then this is not correct. Generally, it's not true. Okay, so that's the inverse, about the inverse transform. And the next topic about the quotient rule is just to say that if you have an equation relating to some quantity that is, they are tensor, and some maybe not. If you have one, like one equation that involves, say, if you know that, just look at the example in equation 420. So the first easiest example, if you have a dot product, so this is a contraction, right? It's right now it's just a summation and it equals to a constant or a scalar, right? If you know, like A is a countervariant vector, B is just a scalar. It doesn't change the coordinate transformation. Then the quotient, we're just saying that the case of I will be transformed like covariant vector. Okay, so that easy to check. And then all the other is just the same. So whatever the equation, the all the different factor tensor except one. Then about the assumption that the equation is valid, then the other one also is corresponding tensor either contrarian or covariant or mixed. So, all right, so that is very straightforward to check it like and this one. So all the other more complicated one is just the same. So you just check that. If you transform this equation in the pi, so you see that becomes a ki prime, ai prime, right? That according to this transformation rule, this is ki, right? Ki prime. This k is unknown, so you don't know how you transform, but a you know how to transform to a, right? And that is partial prime x j, right? And that's how you transform a. If you know a is a contrarian vector, right? But now that you know that you just transform but this is the left hand side. The right hand side is still b because b is assumed to be a scalar, so it doesn't change, right? So that is the I is the I. Just according to the first equation, right? And now then you know that the transformation of so ki is so how you transform this to that is because the other is the same. So you can say this is a sub j, right? So this is not exactly the same thing. You might as well change it to that to make it the same, right? So that by this comparing this to that, kj is this ki. Um, right? And now, according to what we just discussed, the inverse transform is just changing pi to non-pi. Okay, okay, yeah, it's just uh, pi with this, and that is the transformation of a covariant vector, right? So that we know how to show that once you assume that the equation is correct, then following the rule of the known tensor quantity and transform those and use the equation, and whatever is unknown, they show that they transform accordingly. Okay, so all the other equation in 4.20 you can show exactly the same. I think there's some exercise also on homework. Okay. Right. What else in this section? There's an example about the equation motion and the wave equation. And this is just I think it's just the illustration of quotient rule because that assume you have the equation of motion or the fluid equation, I mean wave equation that is a valid physical law, and some quantity is known to be a tensor, then the other quantity is also a tensor according to the equation. Yes, that's one way to look at that. Another way to look at that is all the equation you want to write to describe physics. Hopefully you want to write or express in tensor quantity, and what we want is the form of the equation unchanged, and that is what we call the covariant form. If you want to write the physical law in covariant form. That in classical physics, you probably not paying too much attention to that. Um, but that is very important in relativity. You want to write equation in relativity, either special relativity or general relativity in covariant form, so that you don't need to worry about that this quantity will not be valid after you do a transformation. In special relativity, the transformation includes not just rotation, including the relative frame, so the relative velocity. So that is actually a larger transformation group. So not just rotation, it's rotation combining with the change of velocity, reference frame velocity. So that is what we call the Lorentz, the, or the generalized Lorentz transformation, not just velocity, but velocity plus the rotation. Okay, so you want to write the physical law in covariant form or just express everything in tensor? Okay, I think that's second one.